Hello students, and welcome to test number 3. You have 4 files here on test 3. There is the Permanova PDF, the drug placebo XLSX, the solution PDF, and the question RMD. We're going to start here with the Permanova PDF, and we can see this research article was written in, or was published in 2017. And the name of this article is Some Solutions to the Multivariate Behrens-Fisher Problem for Dissimilarity-Based Analysis. And one of the ideas presented here is potentially very helpful because it will allow us to test a null hypothesis of equality of group centroids in a multivariate case without requiring us to check many conditions. We won't have to check about equality of dispersion, or we won't have to check about multivariate normal distributions or collinearity or things like that. So this presents a simplified way of testing for a difference of group centroids in a multivariate setting. So let's get into this article. And they give you some nice historical background about what's going on here. And they mention how on some of the tests that you could use, you have to have multivariate normal distributions, or you have to have equality of dispersions, or you have to have the sample size being equal, or you have to have more observations than you have variates. And then they mentioned Permanova. So Permanova, there was a couple articles published in 2001 that part of what they did was introduce Permanova. But the way it was originally introduced in 2001, the null hypothesis was that the group centroids were equal and the dispersions were equal. So if you got a low p-value, it could be due to the group dispersions being different, even though the group centroids could be the same. And so what we have here in the next section after this is, so here they're describing the original one. Then they introduce this modified Permanova where the denominator is different now. The denominator here is the within group dispersion for group I, and then you multiply by these constants, or you divide by these constants. And if you read through this, they mention that in the case where the group sizes are equal, then F2 would equal to F1 that you had before. But sometimes the group sizes are not equal, and you would still like to work with the data. You would still like to do a hypothesis test concerning the equality of centroids. And this one will let you do that even if you have different group sizes, and you don't necessarily have to assume that the group dispersions are the same. Now this H here is the hat matrix, which you can get from the data matrix and the normal equations. A G is the Gower matrix, which we'll obtain using the centering matrix and the distance matrix. And if you read through this, you can even compute these VIs using matrix calculations. So it may be better when you're computing the p-values to work with this system. We're not going to do that in this test, but maybe on the next test, we will take a look at these equations and try to implement them into the work that we do. Okay, so let's take a look at our test. Oops, here we are. Here's test 3. So you're going to import this data set, this Excel spreadsheet called drug placebo.xlsx. And when you look at the dimensions, you see there's 38 rows and 4 variables. And the variables are fever, pressure, aches, and group. Now, in such a situation where you have a temperature and a pressure and a count variable, and you're going to do a multivariate analysis, it may be advisable to standardize the variables. That way, there won't be any more units. So you're not adding pounds to centimeters to degrees Celsius. And so the next step here is we're using the scale function from the scales package to redefine fever, aches, and pressure as standard. So we subtract their means, and then scale we divide by their standard deviations. And now when we relook at the data set, we have some negative numbers and things are kind of centered around 0. So we've made somehow these measurements comparable. We can add them together. There's no more units because the units for the standard deviation are the same as the units of the original quantity that you work with. And then we'll be able to add these together. The next step is to create Gower's matrix and then the hat matrix. So along the way, we also have to define some intermediate quantities, like we need the number of observations, little n. Note in the research article, they use capital N, but I like to use small letters, so I'll use small n. Then we need to get the number of distinct groups. So G will be taking the data set, pulling out the group variable, getting the unique values, and computing the length. So there's 2 unique groups. Then we can define the size of each group by using the summarize function. So I say M is assigned to be the data set passed to group by group. And then I pass that to summarize, and N will be counting with the N function. And then I assign N1 and N2 to be the results. Now, in this article, they talk about the hat matrix, the identity matrix, the centering matrix, the unit matrix, etc. And in linear algebra, those vectors, or those matrices and vectors, many of them can be put together by starting with the sum vector. So here Ln is repeating 1 times n. That's the sum vector. One reason you can call it the sum vector is that if you take the inner product with another vector, it will just add up the elements of the vector. And then Jn is the vector, or is the matrix. It's an n by n matrix. All the elements are 1, and you can obtain that as Ln times the transpose of Ln. So I take this outer product of Ln with itself, and it returns the unit matrix Jn. The identity matrix In is the diagonal of the sum vector. And then the centering matrix is the identity matrix minus Jn over n. Now we need a data matrix. So remember, a matrix, all the elements of a matrix are of the same type. But in a data frame, that's not necessarily the case. The columns of a data frame or a tibble can be of different data types. Like you could have a factor variable, a character vector, a numeric vector, a logical vector. All of those could be put together as columns of a tibble. But in a matrix, all the elements have to be of the same type. And so here, I'm taking away the group variable because that's a factor variable. And then I'm turning this into a matrix. So Y will be my data set. And then P is the number of variables, will be the number of columns of Y. And we'll need that later. And then we can get D to be the distance using the Euclidean distance measure. So the distance function will create a distance matrix. It will create a distance matrix. So here it will use the rows and get the distance between rows, and so it will return an n by n matrix. Now, when you use the dist function, it returns a dist object. So you want to turn it back into a matrix, you can do that right here with the double pipe operator. And then the matrix A is minus 1/2 of D times D. Notice this is the Hadamard product. So if you just multiply a matrix with the ordinary multiplication symbol, then it gives you element-wise multiplication. And then Gower's matrix will be the centering matrix times A times the centering matrix. Okay, so that's how we get G. And then we're going to define X to be the group indicator matrix. So I take X and I assign it, or X is assigned to be the data set piped into mutate. And then X1 will be defined as numeric and group equal unique group 1. X2 is as numeric group equal unique group 2. Remember, the double equal sign is a relational operator. So it's going to test whether the two sides are equal and return a true if that happens, or it will return false. And when we convert that to numeric, false becomes 0, true becomes 1. Then I can pipe into dplyr and just select X1 and X2. So the result of this, after we pipe it to matrix, is that we have a matrix with two columns, X1 and X2. Each column has only zeros or 1, depending on whether the row was in group 1 or 2. Then you could assign column names, and then you can get your hat matrix. This comes from the normal equations when you look at regression. So this here is X times the inverse of X prime X times X prime. And that is coming from the normal equations. Then you can work from there to derive or get to the test statistics. So M1 and M2, we need to get the subgroup data. So I'm filtering out the data set just to have the individual groups. And then I need to get the distance matrices just for those groups. So D1 will be N1 pipe to select, where I take away group. Then I get the distance function, and then I turn it into a matrix. And I do the same thing for D2. I take this data frame M2, I deselect the group variable, then I get the distance function, and then I get the matrix. I turn it into a matrix. So now I have these two distance matrices that are just for the individual groups. Then we want to get the within group dispersions. Now the diagonal on those matrices will be 0, so they don't contribute anything. And if you look at what was defined in the research article, they were taking the upper triangular part of these matrices, adding up the squares of all the distances, and then dividing by n1 or ni times ni minus 1. So if I go over the whole matrix, then I'm doing twice of that. So here I divide by 2 to get my V1. On the next test, we'll use the matrix formulations to make the calculation. So in the research article, they showed you how to do these residual matrices to get a V1 and V2, and we'll work with that on the next test. Then you can define the numerator and the denominator of the test statistic. Note here that I have the trace of Hg times H. Now, the trace of a product is equal to the trace of the product in the reverse order as long as both matrix products are defined. And H is a projection matrix, so H squared equals H. And so here, whether I write H or HGH, it'll be the same thing. Then the denominator is given by this form, and then this gives us the F2 statistic. It's the numerator over the denominator. So this is our test statistic. And that's nice. After you get the test statistic, the idea is to use it to compute a p-value. What is the probability of observing what we did under the null hypothesis that the group centroids are equal? Well, we need to create a function that will permute the grouping variable and then recalculate the test statistic after that. So here we go. F perm is going to be a function of x. We're never actually going to use x. We just want it to be a function of some variable. And the first thing we do is we're going to rearrange the group indicator matrix. So we take x. And then what's happening here is I'm rearranging the rows. I'm sampling from 1 to n, where n was the number of rows. I don't replace, and the size is n. So I'm just going to permute the row numbers, and the effect of that is that, remember, x was the group indicator matrix, so I'm just kind of permuting that grouping variable randomly. Then I recompute the hat matrix, and I recompute M1 and D1 and D2. And then I recompute V1 and V2. Then I recompute the numerator and denominator, and I recompute F2. So we're recalculating the test statistic under the assumption that we've just, or not under the assumption, but after we randomly permute the grouping variable. And then we can do that 1,000 times. So I'm using map double, which allows you to map a function onto a vector and return a vector. And then I can look at the p-value as being the sum of how many times the null of x was greater than or equal to f2, and then I divide by the length of null x, and I see that only happened one time. So out of 1,000 random permutations, we only observed one time being bigger than our observed test statistic, and so that's our p-value, 0.001. Right? The next step is to plot a histogram of the permutation statistics just to see what it looked like. So here we have M perm is a tibble with one column called null x. Remember that in tibble, if you just apply a vector and you don't give it a name, the name of that vector will be whatever it would already had. So here when I do ggplot data is M perm, geom histogram, mapping equals AES, x is null x, and y is dot dot density dot dot. And then you could set these other aesthetics. Down here, we're setting these aesthetics. Remember, fill is the inside color, color is the outside boundary. Bins is the number of rectangles. And then we can put a vertical line at the test statistic and add a label for it with geom text. And we can control the labels and the theme, and this is what we get. So this explains what we just did. Or it doesn't explain it, but it presents it to you. Here is the histogram of the statistics, the null statistics computed by random permutations. Okay? So it has this decreasing pattern. Right? And you can see that what we observed is way out here at the right, away from most of the permutations. All right. Now, we're going to look at the principal coordinate analysis plot, which has to do with the eigenvectors of the Gower matrix. So for PCOA, you get the eigenvector. So remember P was 3, we had 3 variables. So I get the first P, or the eigenvectors corresponding to the largest eigenvalues of the Gower matrix. So the eigenfunction returns the eigenvalues and eigenvectors, and it returns them in the order, in descending order of the size of the eigenvalues. So axis 1, axis 2, and axis 3 would be these eigenvectors 1, 2, and 3. Then you can get the relative eigenvalues, which are computed as follows. So I get the eigenvalue 1 and I divide by the sum of the first 3 eigenvalues. And then we're going to create a tibble that has group, will be the data set group information. And then we have axis 1 and axis 2 being these vectors up here. And then we're going to create the PCOA plot, the principal coordinate analysis plot. We use geom point. X goes to axis 1, Y goes to axis 2, and color maps to group. And then we can use scale color manual to control the labels and values and the legend label, which we don't want to have. And then we can get this picture. So this is a picture of what's going on. You had a multivariate data set, and you want to visualize it in 2 dimensions. So PCOA is a visualization technique that allows you to take your multivariate data set and project it onto 2 dimensions and see some structure, hopefully, or some clustering. Now, when you look at this picture, you do see that the drug points, which are in yellow, are more to the left and a little bit lower, and the placebo values are more toward the right and a little bit higher. So you could imagine now that if you randomly selected some of these points to be a yellow or green, what's the chance that you would get this distribution? it's not very high, right? You're not going to just randomly get, half of these or 18 of these to be on the left, or 20 of them to be on the left, and the other ones more towards the right. So this is a pattern where you can see the statistical significance. Now, imagine you had 10 variables. Imagine you had 10 different variables you were measuring, or even just 6. Well, you can't really make a 6-dimensional picture, but you could do a PCOA projected into 2 dimensions and see if you can observe different clustering or different spatial distribution of the groups you're looking at. And the last step here is to combine the 2 plots together, okay, to kind of tell a fuller story of what's happening. So if we use the patchwork package, then we can combine our data to look like this, or our pictures to look like this. On the left, I see the modified permutational multivariate analysis of variance. These were the pseudo F statistics computed under the null hypothesis. And this was the observed value, so that looks significant. And on the right, you see this principal coordinate analysis plot, where you can also see a pattern going on. So these two match up, and they're both a part of the analysis. And from this, you could make the conclusion that there is a difference in the location of the centroids of the drug and the placebo for this multivariate data set. Okay, and lastly, you could practice saving the plot using the code snippet. You could see if you can save your plot. Now, you have to do this. Here, the width should be twice the height in order for these 2 plots to be combined correctly in terms of saving the plot. All right, everybody, that's it for this video. Good luck on the test. Try to get into the research article. Try to learn the software. Try to learn the mathematics. And if you learn this technique, like if you learn PCOA, you learn about scaling the data, you learn about doing permutational multivariate analysis of variance. If you can do all of that, then you're well on your way to getting into a point where you can help analyze data sets that come in biology and medicine. All right, everybody, that's it for this video. Bye-bye.